Okay, guys, so we have to do some preliminary work for our quantum field theory project before we begin the project. So I was doing the work, so I thought, why just not record it? Because you guys can watch it too if you feel like it, and I will get some practice done. So the way that we are going to start is we are going to start with Clifford algebra and Dirac equation. We are going to kind of derive the Dirac equation or guess it because that's the way that Dirac did it. He basically guessed the equation based on the kind of properties he wanted it to have. So to do that, let's just go ahead and first of all recall the relativistic energy momentum relation, which is p mu is equals to e square minus the 3 momentum square is equals to mass squared. Okay, now we have seen that the way that we derive the Klein-Gordon equation from this is by substituting let me just zoom this, by substituting p mu for iota partial mu. Okay, and when we do that, then this relation becomes the Klein-Gordon equation. Partial mu m squared into phi. So the Klein-Gordon equation is nothing but the field theorization of the energy momentum relation, kind of. Okay, now the issue with this equation is that it gives negative energy, so negative probability solutions, and like just a whole bunch of issues with this, and it does not conserve probability. And that's what I meant to say. It does not conserve probability, and there's single particle interpretation problems with this, just a whole lot of things, which you can watch, you can read about it in Sakurai's final chapter, or you can read about it in QFT Gifted by Brindle. They do a pretty good job explaining of what is wrong with this and why do we need an equation which should be first order. Okay, so Dirac basically had the insight to see that all the things that were wrong with the Klein-Gordon equation could be set right if he had a first degree equation. So as you can see here, we have a second degree equation. Okay, so the question that he asked was, can we take, but to make a first degree equation out of this, what we would need is a kind of a square root of the operator, right? We would need to take the square root of a derivative operator. So for example, I know we physicists have been doing this for, I don't know, since our childhoods, but the square root of this, right? What would it even mean to take the square root of d squared over dx squared, for example, right? Nobody had done that up until then. Okay, so how do you take the square root of a differential operator? Okay, so if he could take the square root of this, then he could come up with a single degree equation. Okay, so what he needed was, this is Dirac guessing. Okay, so what he needed was a, let's just what he needed in this, in place of this partial mu, okay, in place of this was something like, let's say, gamma mu partial mu squared. If he could do something like this, right, then he has basically then he can just take the square root of this, right? So this, he needed some kind of entities, gamma mu's, okay, which when multiplied with the differential operator can be used to take the square root of the box operator, basically. Okay, now he went on and asked the question, what properties must these gamma matrices have? Sorry, spoiler alert. First of all, right now we are not assuming they are matrices. So what properties must these gammas have in order to satisfy this? Okay, in order to be used to construct a square root of the differential operator. Now the first thing to note is that they cannot be ordinary numbers. Okay, because if they are ordinary numbers, then ordinary numbers, all scalars commute, right? And you basically get the same thing back. So they cannot be ordinary numbers. Okay, they have to be matrices. Now what dimension of matrices, that we will come to, but for right now just keep in mind that they cannot be numbers, so they have to be matrices. So let me just go ahead and show you some more, like why that cannot be the case, why they cannot be numbers. So just consider this quantity that I have. Okay, then we know that we can write this quantity as gamma mu, gamma nu, partial mu, partial nu. Let me just, okay, where of course what I have done is I have simply like expanded the square root, kind of. Okay, now this part of it, gamma mu, gamma nu, consider this one. Okay, this is some two indices object. Okay, and we know that we can write any such objects as a sum of symmetric and anti-symmetric parts. Okay, so let me just go ahead and break this down into symmetric and anti-symmetric parts. So this is the anti-symmetric part of it, and then this is the symmetric part of it, and then I have partial mu, partial nu, sorry, partial mu, partial nu. Okay, so let's just go ahead and multiply this with the inner quantities, and what we get is half gamma mu, gamma nu minus gamma nu, gamma mu, partial nu plus half gamma mu, gamma nu plus gamma nu, gamma mu, partial mu, partial nu. Now this is anti-symmetric, this quantity is anti-symmetric, but we know that this is symmetric, right? Because the derivatives commute. So this is a symmetric part, this is anti-symmetric part, and we know that whenever you contract with an anti-symmetric part with the symmetric, what you get is 0. So this part vanishes, and what you end up with is gamma mu, gamma nu, partial mu, partial nu is equals to half gamma mu, gamma nu plus gamma nu, gamma mu, partial mu, partial nu. Okay, so this is equal to, from where, like the way that we took it from above, is equals to gamma mu, partial mu squared. Okay, now for this to be equal to partial mu, partial nu, which was our original goal, like for this to be equal to this, what do I need? Can you guess it? Okay, let me just go ahead and tell you. So for this to be equal, what I need is this quantity. Okay, just let me help you a bit more. This here, of course, we can write it as eta mu nu, partial nu, partial nu. right? We can write it like this, right? Now for these two quantities to be equal, these two quantities, what I need is I need the anti-commutators of the gamma matrices to be, we know how we define it. Let me just go ahead and write it. Gamma nu anti-commutator is defined like this: gamma nu less gamma nu gamma. Why am I writing partials? Okay, so this is equal to, if this is equals to 2 eta mu nu, of course the identity matrix, then this equation is satisfied. Okay, and from here we get the commutation relations for the gamma matrices, and this is called the Clifford algebra. So these are the properties, or this is the commutation relation that our matrices must have in order to allow us to take the square root of the operator, which was our original goal. Okay, so just keep this in mind. Now since we have this, we are gonna go ahead and okay, so just keep in mind that gamma mu here are matrices, and the thing that it will operate on will be a 4-component object in this case. Okay, so we will come back to that, but for now let's just go ahead and extract some consequences of the algebra. Okay, so let's just it will allow us to get some practice and at the same time get some insight into what's happening. Okay, so let's just go ahead and see what happens to the algebra when mu and nu are equal and both are 0. Okay, so when mu and nu are equal, this is your algebra. So you can see when mu and nu are equal, then this is basically 2 times gamma rho, right? But 2 and 2 on both sides cancel, and here you have eta 0, okay, which we know in the convention that we use is +1. So in short, what you get is gamma naught squared is equals to eta naught is equals to 1. Okay, so this is your 0th component, or time component if you want. Now the second case that can be is mu is equals to nu, but that is equals to, let's say, some spatial component. Okay, so what happens in that case is, again, we get the same thing. Gamma naught square will be equal to eta I, but now I is -1. Okay, so this is another thing that you can get from it. And the third case, of course, that we can have is when mu and nu are not equal. So when mu is not equal to nu, then what we have is, let me just go ahead and copy paste the algebra for you. Okay, so when mu does not equal to nu, then we know that this part is 0. Okay, so if this part is 0, then that implies that when mu and nu are not equal, then gamma mu is just equal to minus gamma mu. Okay, so this is the third property. Now what can be the minimum matrix dimension that we can have? So for that, again, you can go to Sakurai on QFT gifted other books like Pesker and Schroeder. I'm not sure if they have the discussion in it, but due to various reasons which you can look up in different books, we must have a 4x4 object in the gammas. Okay, so we need 4 matrices, and due to these properties that we derive, this and this, okay, and some other properties that you can look up. The entity which satisfies all of these properties must be a 4 by 4 dimension object, which means since this is a 4 by 4 dimensional object, so let me just, so if gamma mu is a 4 by 4 dimensional object acting on some psi, then the only way that this can act on it is if they both have the same dimensions, right? So psi must be a 4 dimensional object, okay, and that's where we get the 4 dimensional spinner. Okay, so now our wave function basically has 4 components. Let's write this down as 4 components. And this, if you think about it deeply, please do, it's very beautiful in a way. Why? Because it's almost like the entity that you're constructing, like let's say electron, proton, whatever you have, right? It needs to have the exact same dimensions as the space-time components to survive in space-time or talk to all of space-time, kind of like, you have 4 components for psi, and then you have 4 components of space-time. So please do look up into the the deep meaning of what this means and how it cannot be any other way. So okay, now I'm just gonna go ahead, and what we have done so far is we have derived the commutation relations for gammas. But what are gammas? Okay, what does the gammas equal to? So again, the properties that I have listed and some others that you can look up, all of them combined make you tells you that the gamma must have this form. Let me just go ahead and write it, and this is the standard or Dirac representation. Okay, so in the Dirac representation, also called the standard representation, your gammas are nothing but basically nesting beds for the Pauli matrices. Okay, so let me just go ahead and write them. So gamma naught in this is equals to the identity matrix 1 0 0 minus the identity matrix. Keep in mind that 1 here is not the number 1, it's a 2 by 2 identity matrix, otherwise this will be a 2 by 2 matrix. Okay, and similarly the other gammas are simply, as I said, nesting beds for the Pauli operators. Okay, so this is it, and like this is basically your Dirac representation. Okay, if you want to recall, let me just help you. You can skip this part, but just to help you recall some facts, Pauli matrices are given by sigma 1 is 0 1 1 0. They are 2 by 2 non-diagonal traceless matrices. Gamma 1 is equals to this 2 by 2 anti-emission traceless matrices. So sigma 1 is equals to this, and then sigma 2 is equals to 0 minus iota 0, and then sigma 3 is equals to 1 0 0 minus 1. Okay, now you can go ahead and, as an exercise, use these matrices or this representation to check or verify that these 3 properties that we needed are satisfied. And yeah, that's basically, take it as a homework. So we have constructed, or we have found the gamma matrices that are needed for us to, in order to take the square root of the Klein-Gordon equation. Okay, so Dirac equation is nothing but the square root of the Klein-Gordon equation. So let me just go ahead and list some properties of gamma matrices that we will use when we do the project. Okay, the first one is that it's Hermitian. Okay, one of the metrics is Hermitian, while the other 3 are anti-Hermitian. Okay, so gamma naught, again note that the beauty of it is that just like the time component, the time matrix kind of here is behaving very differently, right? While the other three behave different. So this is equals to gamma naught. While if you take the Hermitian conjugate of any other matrix, okay, you get a minus sign. Okay, this is one property, or the hermiticity property, and this both of these can be written down into one property, and that is gamma mu dagger is equals to gamma naught gamma nu gamma naught. Okay, so this is basically just contains both of these properties. Then another property that we have is let's just go ahead and see the traces. Okay, what the trace of the matrices are, and we know that the trace for the Pauli matrices is 0. Okay, the trace of any Pauli matrix is 0, and by consequence the trace of any gamma matrix is also 0. Okay, except for the identity matrix, of course. Okay, so the identity matrix is a 4 by 4 matrix, therefore the trace of the identity matrix is 1. Okay, while the trace of any gamma matrix is 0. Okay, while if you take the trace of a product of gamma matrices, let me just move them here. If you take the trace of a product of any gamma matrices, what you get is 4 eta mu nu. Okay, so what that means is if the matrices are the same matrix, only then the trace survives. So if not, then you get a 0. Okay, so if mu and nu are equal, only in that case do you get a non-zero contribution. Okay, and another thing to keep in mind is the trace of any odd number of gamma matrices is always 0. Okay, so now what we have is we have the trace for 2 matrices, we have the trace for 3, 5, 7, 9 matrices, while we also have the trace for, let's just you can also get the there is a neat formula for the trace of 4 matrices too, you can just look it up. Okay, and then we have contractions. All of these will be used in our project, so it's best to just go over them. So contraction of identities, you have gamma mu contracted with gamma mu, and this is equals to 4. Okay, any matrix contracted with itself or its dual is equal to 4. Okay, while if you contract 3 matrices, again I just start here, if you contract 3 matrices like this, okay, what you get is minus 2 gamma mu. Okay, so the matrix that is in the middle of the duals of the matrices which are dual of each other will give you minus 2 times the matrix. Okay, and if you do that with 4 matrices, we have 3 matrices, then let's say we have gamma mu, gamma nu, gamma rho, gamma mu. So what I'm doing is I'm sandwiching 2 matrices in, right now, 2 matrices between the duals. Then what you get is you get the Minkowski metric. Okay, cool. Now here comes the most important metrics. Okay, not like the most important, but so far in the identities or the properties, the most important one, and that is it's not even like a property or whatever, but kind of like a construction that we have made. So we define a matrix gamma 5 as the product of all the matrices. Okay, so we put an iota here, and then what we have is basically gamma naught, gamma 1, gamma 2, gamma 3. Okay, so this is a matrix that we define, and you can again do the calculation to find out that this is nothing but 0 1 1 0. Okay, and this allows us to construct the what we call the chiral representation or the veil representation, okay, which is something that we use to project left-handed and right-handed wheel spinners, which are the fundamental objects in the standard model. So this is very important. Okay, and you can just go ahead and do that. So now we move on to the veil representation. In the veil representation, okay, gamma 5 changes its form. Okay, so all other gammas are same. Gamma naught is your 0 1 1 0, while your gamma i's are the same polymatrices, while your gamma 5 is minus 1 0 0 1. Okay, so gamma 0 or gamma 5, both of these change their form, while the spatial gamma matrices kind of are the same as they were previously. Okay, in this representation, again, we construct two projectors, which you can do. Let me just go ahead and write them down. We call it PL, which is the identity matrix minus gamma 5 divided by 2. Okay, so if I subtract the gamma 5 from the identity matrix, what I get is 1 minus 1, that's 2, and here 1 minus 1, that's 0. So I get 2 here and I get 0 everywhere else. Okay, but that 2 divided by this 2 is basically 1. So this projector is 1 0 0 0. Okay, similarly, I construct another projector that I call PR, and this time I do it by adding gamma 5. Okay, and as you can guess, in this case I get zeros everywhere except the lower right column, lower right row, lower right entries. Okay, so this is so far the Clifford algebra and some representations thereof. Keep in mind that of course the representations are not fundamental. Okay, you can just you can change between representation simply by a unitary transformation. Okay, so you can go from any representation to any other by simply doing this. Okay, but what's invariant is the algebra. Okay, so the Clifford algebra are the main entities or the main characters here. So far we have seen the Clifford algebras and some properties of the gamma matrices and some representations thereof. Now we are gonna derive the Dirac equation from a Lagrangian. Okay, and we will move forward from there.